This figure taken from a textbook shows the electron transfer in complex 3. It is not that clear. I will explain it in a better way in the slide after next. As you see in this figure, complex 3 contains 2 copies of the enzyme, and each copy contains electron carriers. It contains 2 of the cytochromes of the B type, what we call BL and BH. I explained what we mean by BL and BH earlier. There is an iron sulfur cluster and involved in a protein called the Rayisky iron sulfur cluster, named after the one who discovered this protein, and there is cytochrome C1. How electrons pass in complex 3? This is explained through what we call the Q cycle. And before I explain the cycle, I would like to point out that there are 2 independent binding sites for the coenzyme Q or ubiquinone. One which is known as a Q node that binds QH2 and is located close to the intermembrane space, and one which is known as a QI, which binds both ubiquinone Q as well as the semiquinone and is located near the matrix. The Q cycle is made up of 2 phases. In the first phase, as you see in the upper part of the figure, QH2 from complex 1 binds to the Q node site, okay, and it transfers one of its electrons to the iron sulfur cluster and releases 2 protons and forming semiquinone. Now that electron from the iron sulfur cluster will reduce cytochrome C1 and from there to cytochrome C to complex 4. Now what happens to the semiquinone? The semiquinone transfers the electron to BL, then to BH, forming Q. Q can move now to QI. By the way, the semiquinone is immobile. It cannot move across the membrane. So once Q is formed, it can move in the membrane to reach the other binding site QI, and there the electron will be used to reduce Q to semiquinone. This completes the first phase of the Q cycle. What about the second phase? In the second phase, again, one electron, another molecule of QH2 is used, and one electron will be used to reduce C1, as I said earlier. In other words, the QH2 will lose 1 electron to iron sulfur protein, to cytochrome C1, then to cytochrome C, then to complex 4. And the semiquinone now formed, again, will lose its electron to BL, then to BH, and eventually it will reduce the semiquinone formed in the first phase to QH2. So as you see here, it's true we use 2 molecules of a QH2 in phase 1 and phase 2, but one of these molecules was regenerated in phase 2. Complex 4 is called cytochrome C oxidase, and it is made up of 2 functional units. Each unit contains the 3 subunits, 1, 2, and 3, as you will see in the next slide. And this complex receives the electrons from cytochrome C, and we will use them in reducing oxygen to water. Oxygen, as I said, is the terminal electron acceptor in the electron transport chain. This slide shows the electron carriers in these subunits. Subunit has 3 redox centers in A, in M, in A3, and the copper atom CuB. Subunit 2, there are 2 copper atoms forming a redox center called CuA, while there are no electron carriers in subunit 3. This figure shows the pathway of electrons in complex 4. The electrons coming from cytochrome C, okay, they will go to the CuA, then to cytochrome A, then to cytochrome A3, to CuB, and eventually to reduce oxygen to water. With every electron translocated, there is 1 proton transported across the inner membrane from the inner side of the membrane to the outer side of the membrane. So this complex is associated with the transport of 2 protons from the inner side to the outer side of the membrane. therefore is associated with the production of the energy, as you will learn later. This figure shows the two functional units that make up cytochrome C oxidase. These complexes, which I have discussed earlier, in particular complex 1 and 3 and 4, they act as energy conversion device to harness this energy change. How is this energy conserved? It's conserved by bumping protons from the inner side of the membrane, of the mitochondrial membrane, and from the matrix side to the outer side, which is the intermembrane space, creating a proton gradient. And the energy of this proton gradient is called as the proton motive force. How ATP is formed, that was explained by a scientist called Mitchell in a theory called the chemiosmotic theory, for which he got Nobel Prize in the year 1978. And that theory postulates that the free energy in the electron transport is conserved by pumping protons to the intermembrane space to create a gradient. And this gradient will later be used for the production of ATP, as you will see in the coming slides. In other words, what happens? The oxidation of an ADPH or the oxidation of succinate to fumarate and the formation of ETH2 is coupled to the phosphorylation of ADP. This oxidation is coupled to the phosphorylation of ADP. These are two distinct processes, as I said. In the oxidation, we have oxidation of an ADH to an AD plus or QH2 to Q. And in the phosphorylation of ADP, we have the formation of ATP. In this slide, it's clear that oxygen consumed only with ADP and excess inorganic phosphate. So when ATP is phosphorylated to ATP, that's when oxygen will be consumed. If we use uncouplers of oxidative phosphorylation, such as dinitrophenols, what do we mean by uncouplers of oxidative phosphorylation? These uncouplers, they make the membrane permeable to protons. That's to say, you can't create a proton gradient across the membrane when you have these uncouplers. Therefore, the electron transport will take place. Electrons will go in the electron transport chain, but this will not be accompanied by the formation of ATP.